Hi everyone, welcome back. What we're going to do in this video is start talking about acids and bases. This is from chapter 3 in our textbook, okay? So now you are familiar with the concept of acids and bases, but I also want to let you know that for the purposes of organic chemistry, we are going to redefine an acid and a base so that it is more appropriate for our discussions here. Okay, so to start off, I think I want to talk about maybe some definitions of acids and bases that you guys are already aware of. Okay, so acids and bases have been defined in several ways. So one of the definitions, like one of the earlier definitions of acids and bases, was given by Arrhenius. Okay, and we call these Arrhenius acids and bases. And the way Arrhenius defined acids and bases is acids are proton donors, or they generate protons in solution. I guess that is better. So generate proton in solution. Okay. Now, key point here. This is H plus, that is what we are calling a proton here, okay? So this is a hydrogen atom that is missing its electron, okay? That is the proton that we're talking about. We are not talking about the subatomic particle proton, like the proton in the nucleus. That is not what we're referring to here. So acids generate protons in solution. Base, on the other hand, was defined as something that would generate a hydroxide in solution, okay? And this is the definition of acids and bases that we are all first introduced to in general chemistry, okay? So examples of an acid, I'm sure if I had asked you to like shout it out, all of you would say hydrochloric acid, so HCl, okay, or maybe sulfuric acid, nitric acid, any of those, okay? Those would all be examples of acids, because when you have HCl, what we know is this in solution, it can give us H plus and then Cl minus, okay? This bond between the H and the Cl, it is polarized. The hydrogen is del positive, the chlorine is del negative. And so essentially, again, in terms of organic chemistry, the way we would show something like this is these electrons are taken up by chlorine, okay? Both electrons in this bond, they go to the chlorine, so we get a Cl minus. Okay, this chloride ion has 8 electrons around it, and the hydrogen is now missing its electron. So it generates protons in solution. So in aqueous solutions, we have protons generated. So it's an acid. Similarly, for a base, again, I think a lot of you would think about something like sodium hydroxide, okay? Because when you are in solution, then sodium hydroxide, what we know is that in solution, this would give us sodium ions, and it would give us hydroxide ions, okay? So it generates hydroxides in solution, and so we can call it a base. So it's not really limited to sodium hydroxide, but let's say potassium hydroxide or calcium hydroxide. These could all be called bases by that definition, because once you put them in water, once you dissolve them in water, they would all generate hydroxide ions for you. Okay, so that's the definition for, or that is the Arrhenius definition of an acid and a base. But then this definition has issues, it has limitations to it. So for example, if I were to ask you about ammonia, which is NH3, another popular molecule that you see in Gen Chem, okay? Ammonia, now the nitrogen has a lone pair on it, that is what I'm showing here, okay? Is this an acid or a base? And I know students say this is a base, but then based on the Arrhenius definition, it doesn't have hydroxide in it, okay? So then how could we call it a base, okay? So there are limitations to how acids and bases are defined in by Arrhenius. So to cover that, okay, and to basically expand the scope of what an acid is and what a base is, there were other definitions that were basically proposed, and we're going to talk about one of the famous definitions, or like the more important, more expansive definitions of acids and bases here, and this would cover the basis of a lot of our discussion, and this is the Bronsted Lowry definition. Okay, the Bronsted Lowry definition of acids and bases. Now, in the Bronsted Lowry definition, an acid is defined as a proton. Again, we're talking about H plus, a proton donor, while a base is defined as a proton acceptor. So you notice how there is no dependence on the hydroxide. So the definition of an acid pretty much remains the same. It is still related to being able to produce protons or generate protons in solution, or being able to donate a proton. But a base is defined, but the base is also defined based on the proton here. So it is defined as something that is a proton acceptor. Okay, so let's look at an example of how this would work. And in fact, we will try to include ammonia here. Okay, so again, examples: HCl, very standard. Example, sodium hydroxide. So let's see how sodium hydroxide and HCl still continue to be an acid and base in this new definition, or under this new definition. Okay, so if we have HCl and we have sodium hydroxide. Now, just a quick review of chapter 1, where we talked about bonds, okay? Covalent bonds, ionic bonds. So hopefully, based on that information there, you should realize that this is a polar covalent bond here, okay? So this is a polar covalent bond, but the bond between the sodium and the hydroxide, this is an ionic bond, okay? That's more of an ionic bond. So this oxygen has 3 lone pairs on it. Okay, it has 3 lone pairs on it. The sodium and the oxygen bond is an ionic bond, but also realize that this bond is something like this. The oxygen hydrogen bond is a polar covalent bond. Okay, so the oxygen has 3 lone pairs, and so it has a negative charge. So sodium hydroxide would be an example of a compound which has an ionic bond, and it also has a covalent bond, okay, a polar covalent bond in it. Okay, so we have HCl and we have sodium hydroxide. When you combine these two, what you know from Gen Chem is that sodium hydroxide, a base, can react with HCl, an acid, to give you water and sodium chloride. Okay, so that is what you will get. Acid and base react to give you water and a salt. In fact, these are both strong acids and strong bases. Again, that is not the purpose here. And these are not the sort of acids that we will be looking at. These are inorganic acids. We will not be talking about inorganic acids. We will talk about organic acids. But we will use this information here to develop our definition of organic acids and what would be an acid, what would be a strong acid, what would be a weak acid. We'll talk about all of those. Okay, so now when you have sodium hydroxide and HCl, you notice that these are reacting. And in this acid-base chemistry, especially for organic chemistry purposes, we have to show electron push arrows to show these reactions. Okay, what is happening here? So this is our acid and this is our base. So acid is a proton donor. It donates a proton. Base is a proton acceptor. So in this particular case, what happens is we have H, which is del positive. The chlorine is del negative. This is our acid. And we have sodium and hydroxide ion. So the hydroxide ion uses its lone pair to grab or basically abstract this proton. Okay, basically takes away that proton. Now this hydrogen here has a bond to it. That means it has 2 electrons on it already or around it. Its octet is complete. The hydroxide ion is bringing 2 more electrons. Okay, this electron push is 2 more electrons coming in to abstract that proton or grab that proton. Now, the hydrogen would definitely not want 2 plus 2, 4 electrons around it. So as the hydroxide ion is abstracting that proton, what would happen is the electrons in this bond, these go to the chlorine. Now, chlorine would have 3 lone pairs around it. Now, this is also, I just want to mention, this is also a point where we are going to be moving away from showing all the electron pairs and everything. Like, we'll do it for a little bit, but we will be moving away. And after that, it is basically understood that the Lewis structure of the halogen should have 3 lone pairs around it. Okay, so hydroxide abstracts the proton. The bond between the H and the Cl simultaneously, okay, at the same time, simultaneously moves to the chlorine, because the hydrogen does not want to exceed its octet. And so what we've done here is we've formed a new bond between this oxygen and this hydrogen. And so we will have the oxygen. It had 3 lone pairs initially. It used one of those lone pairs, so it should have 2 lone pairs on it. And that oxygen was connected to this hydrogen. So we have 1 hydrogen on it. And that oxygen now abstracted another hydrogen, so it has the 2nd hydrogen on it. And basically what we have here is our water molecule. Now, the sodium ion here, notice this was just an ionic bond. That means there were 2 charges that were attracted to each other. There isn't like a physical bond between them. It is just an attraction between 2 charges, or 2 oppositely charged species, to be more precise. Okay, so that ionic bond, okay, so there isn't like a real bond, like a physical bond between them, like that we would draw, like a covalent bond. Okay, so it was just a force of attraction, and the sodium ion was pretty much balancing the charge for this oxygen ion. Because the oxygen was negatively charged, the sodium ion was positive. So once that happens, based on the electron push here, the chlorine would now get another electron. So we will get a chloride ion. Okay, so that chlorine would be negatively charged. And so the sodium ion, which was initially balancing the charge with the oxygen atom, now goes with the chloride ion. And that gives you the sodium chloride salt that we're getting. Now, I think what I'm trying to say here is just to emphasize here, the sodium ion, these ions, they have a role to play. But for our purposes, this is just a spectator ion, which is balancing the charge. okay? We will not think about them beyond that. They are just something to balance the negative charge on the base. That is what they're doing here. So when we do these reactions now, so we can show the electron push. That is what I was trying to say. And this electron push that we're showing here, this is called the mechanism of an acid-base reaction. So mechanism is basically, it gives you details of what sort of electron movements happen so that you get to the products. In fact, there's more to the mechanism, and we will discuss mechanisms in chapter 6 later. Okay, but this, at least the electron push that you're seeing here, it gives you some insight into, okay, how did I get water molecule and how did the sodium chloride form? Okay, now another point here, in an acid-base reaction under the Bronsted Lowry definition, when an acid reacts with a base, okay, the acid is losing its proton. The acid is HCl. It will lose its proton, and the species that results from that loss of the proton, which is the chloride ion here, okay, not the sodium, because the sodium is just balancing the charge, but they are one species together. This chloride ion, that chloride ion is called a conjugate, sorry, I'll need more space. So this chloride ion is called a conjugate base. Okay, that chloride ion is called the conjugate base. Similarly, when the base, so in this particular case, the base, the real base is the hydroxide. When the base accepts the proton, what you get, the resulting species here, this is called a conjugate acid. Okay, that's called the conjugate acid. And I'm going to add those definitions here. So conjugate base is species obtained when acid loses its proton. That's the conjugate base. And then we have conjugate acid. This is the species obtained when base accepts a proton. Okay, so those are two species. So in an acid-base equation, essentially we have four entities involved. We have the acid, we have the base. On our reactant side, acid reacts with base to give you the conjugate acid and the conjugate base. So there is an acid and a base on both sides. We'll go into the details in subsequent videos, but I also want to show you how in this definition ammonia can be a base now. Okay, so let's look at that also, and we'll try to do something similar and just review or reintroduce you to these terms, you know, and define an acid, base, conjugate acid, conjugate base. So let's consider another scenario where we have HCl, and now we have ammonia. Okay, so nitrogen has that lone pair on it. HCl is the acid here. Ammonia is the base. Okay, now acid is a proton donor, base is a proton acceptor. Now the base needs electrons to accept the proton. So in case of ammonia, where are the electrons that it could use to accept the proton from the acid. The ammonia needs an electron, a pair, like a lone pair, to accept the proton. So if you look at it, it is the lone pair on the nitrogen. So what happens here is the lone pair on the nitrogen grabs that proton from the acid, because again, this H is del plus and the chlorine is del negative, partial positive, partial negative. You do not have to show these charges, okay? But I'm just showing it for like clarity here. Accepts the proton, electrons from that bond go to the chlorine, pretty similar to what we did earlier, okay? And so in this particular case, we will get the nitrogen had 3 hydrogens. Now it has grabbed another proton. So we will get NH3 with another hydrogen. Now the nitrogen has 4 bonds to it. This is actually the ammonium ion. That is what we've drawn here. The nitrogen has 4 bonds to it. So it must have a formal charge of +1. Again, going back to the bonding patterns for nitrogen. And plus the chloride came out, so we will get a Cl minus. Okay, that would be our acid-base equation here, and the electron push that corroborates with that acid-base equation. Okay, now acid will lose its proton to give you the conjugate base. So in this particular case, the base is going to be the chloride again. The base, when it accepts the proton or when it adds the proton, it becomes the conjugate acid. So that means this ammonium ion here is the conjugate acid. Okay, so I hope that helps. Okay, now the other thing that I want to basically, so the reason we did this is to show that, okay, now under Bronsted Lowry definition, ammonia is also a proton acceptor, which means it qualifies as a base. So we will say that ammonia is a Bronsted Lowry base. Sodium hydroxide is also a Bronsted Lowry base. Okay, so the Bronsted Lowry definition, as you can see, it is more expansive, or it's like basically includes a lot more chemical entities as acids and bases. Now, it is possible that a molecule would act as an acid as well as a base, like the same molecule. That is possible based on the situation. So, for example, if we look at it, HCl can react with water. Okay, we know HCl is an acid. This will be our base. HCl reacts with water, and in this particular case, again, I think I want to make a clarification here. At this point, I think we're dealing with some of these inorganic acids. So you might wonder as to how do I know which one's the acid and which one's the base. Okay, so we will talk about some of these things later. But at this point, what I'm doing is, if I see an inorganic acid like HCl, nitric acid, sulfuric acid, anything like that, or HBr, HI, any of those species, I'm just taking that as an acid and just moving along with that. Okay, so the HCl is an acid. Water could act as a base because it has lone pairs on it. The oxygen in water molecule has lone pairs on it. So the water molecule abstracts the proton from HCl. Electrons go to the Cl. And this will now give us, oxygen had 2 hydrogens around it. So it will give us OH2 with a formal charge and 1 lone pair. This species is essentially hydronium ion. That's what we call it. H3O plus is the hydronium ion. And if you think about it, a hydronium ion is nothing but a proton sitting on a water molecule or connected to a water molecule. And we use a hydronium ion as a general representation for an acid. So in organic chemistry, we will never write H plus. We'll usually write an acid as H3O plus to say that that is an acid. Okay, that and plus we will get chloride. So when the acid loses its proton, it will give you the conjugate base. And when the base accepts the proton, it will give you the conjugate acid. Okay, so the H3O plus here is the hydronium ion. So this is an example where the water acted as a base. But we could have another example where we have water molecule and plus we have let's say sodium NaNH2. I'm just making up a base, okay, here, but this is a base that we will see later, okay? So let's say sodium amide and water molecule here. If you have these two, now you would notice that, okay, you have water where oxygen has lone pairs on it, and you have this other species which has a nitrogen with a negative charge on it, okay? And that is basically, it has lone pairs on it. So you have two species which have like lone pairs on it, on them. So which one would be the acid, which one would be the base? Just as a rule of thumb, whenever you see something like this, now again, there are exceptions to this rule, but just as a rule of thumb, whenever you see something like this, use the negatively charged species as your base, okay, just as a rule of thumb. So we're going to say water in this case is our acid, and this is our base. And so the base is going to go and abstract a proton. So the nitrogen uses its lone pairs to abstract the proton. And I guess something that I did not mention, very similar to resonance, these electron push arrows have a lot of significance. They always start with the source of electrons, they end where the destination is. Okay, you have to show it very carefully. Starts with the source, goes to the atom that's getting that electron pair. Okay, so when we do this, we will get now water is losing its proton. Oxygen will have 3 lone pairs around it. So we're going to get sodium and hydroxide now. We'll get a hydroxide ion. Nitrogen here. So the sodium was just balancing charge here. It was with the nitrogen earlier, and now it's with the oxygen. And plus, the nitrogen had 2 hydrogens to it and 2 lone pairs. Now it abstracted a proton. We will get a nitrogen with 3 hydrogens and 1 lone pair. Okay, that would be our conjugate acid. So this is our conjugate acid, and this is our conjugate base. Okay, going forward, what we're going to do is we will just use Ca for the conjugate acid and Cb for the conjugate base. Okay, Ca would stand for conjugate acid and Cb would be the conjugate base. So here you see an example where the same molecule, depending on the scenario, it could either act as a base or as an acid. Okay, so that's some determination that we have to make again. So I know it turned out to be a slightly lengthy video, but I tried showing you some examples, you know, working through the mechanistics and everything here, like the electron push and all of that. But we will discuss other aspects of acidity and basicity in subsequent videos. Bye.